Good morning, good morning. All right. I'm sleepy. I got home very late last night. So almost didn't do this today, but I was just gonna do a short session. Because I gotta go. It's my birthday weekend. It is tomorrow. And got a lot of birthday stuff planned. I'm gonna tweet. No, I'm gonna blue sky. Wait, where do we set the category? No, category set. It's really hard for me to tell how loud that is. I wanted to take my audio output from OBS. And how to do that? Let's see if I can do that real quick. No, that's audio capture, output audio, speaker. Okay, let's try this out. Now I'm getting audio from 2 different sources. Now I need to send this to not my headphones. Yeah, I'm not gonna worry about that right now. It sounds a little loud. I don't know. Alright. We're gonna do some Willow. Last time I had summarized quantum computers as a cloud of possibilities. Apparently that's the last thing I wrote. I must have read that somewhere. That's brilliant. I don't have a lot of time today, so what I'm gonna do real quick is just try to understand the methods of error correction, no cloning, and just very basic hardware stuff like the difference between ions and quantinuum. My understanding now after last week of reading this was that this report is basically just saying they have new ways of error correction. The groundbreaking part of this research is they reduce errors exponentially as they scale up, essentially. And just that it's able to give them a more reliable measure of the speed, but not so that they've actually made like this chip. I don't think this chip exists as a consumer product, as a design ready product is my understanding yet, but I was focusing more on the general knowledge than this specific chip. Okay, I'm gonna get into it. I'm gonna get into it real quick. I'm gonna start over on the article real quick and just kind of double check I'm understanding everything going on here. Actually, I'm going to answer some text. Sorry. I don't know if you can hear that. I need to get that to not go off. That's my watch. Oh, my hair is insane right now. Alright. I fucked around for 10 minutes. Okay. Let me get my notes open. Today, I'm delighted to announce Willow, our latest quantum chip. Willow has state-of-the-art performance across a number of metrics, enabling two major achievements. The first is that Willow can reduce errors exponentially as we scale up using more qubits. This cracks a key challenge in quantum error correction that the field has pursued for almost 30 years. Okay, yeah, we generally understand this. Errors are coming from decoherence. I wanted to set up Claude on the stream. Hold on. I'm gonna disappear. One sec. I've been hearing such good things about Claude. I've been hearing that it's better than ChatGPT. So, I haven't used it yet. This is my first test. Sorry, just signing in. Should be getting signed in. What information does it put here? This is my email address. That's public. That's on my website. By the way, I have a website now. I don't want to be logged in the browser. Yeah, don't do that. Just log me in on this website. Right now, Claude doesn't have any information about me, but it could in the future. Alright, I think this is good to send and finish today. Okay. I feel like this music's a bit loud. Okay, yeah, I'm gonna try using some Claude. I don't know how good it is. So let's just double check that statement I just made. Correction in quantum computers is when avoiding decoherence, or maybe I should say unexpected decoherence, right? Better that. Expect errors that occur due to. Well, that is what I was asking. It works by encoding quantum information redundantly across multiple physical qubits to create more robust logical qubits. And that was something I was struggling to. That's a massive shadow. How do I not get a massive shadow? That's pretty good. Okay, yeah. I mean, this is what I thought. There's a lot of questions I still have about redundancies, like why is redundancy so difficult in quantum computers? And they said because of linearity, redundancy is very difficult in quantum computers, but I don't completely understand why that is. ChatGPT was struggling to explain that to me. We're gonna see if Cloud can explain that. Think of it like having multiple copies of information. If one copy gets corrupted, you can still... Yeah, this is redundancy. It's the same thing as like on the space shuttle, there was 100 computers. That wasn't... I don't know. What was it? 4 computers that NASA used? Actually, I think I'm thinking of Apollo as well. For navigation. So, if anything happened to them, yeah, they have a failsafe. I'm sorry, I'm so slow with words this morning. However, quantum error correction is more complex because you can't simply make direct conclusions. Yeah, due to the no cloning theorem. That's what I wanted to start with today was... Well, actually, I want to start with methods of error correction, and then we get to no cloning. But let's go ahead and go to no cloning first. Uses sophisticated encoding schemes that spread quantum information across multiple entangled physical qubits. The main sources of errors that quantum error correction address include decoherence, loss of quantum information to the environment, gate errors, imperfect quantum operations, measurement errors, physical defects in the qubits themselves. Would you like me to explain more? Yeah, we'll get to that. First help me. Gate errors. Gates are just operators, the same thing you see in like logic design. Design gates. So you know, in normal computers, you have these logic gates. This is the basis of computer operations, essentially. We're not gonna go over this today. This is, if you know this, great. If you don't know this, maybe one day I'll go over logic systems. If we need to know this for further quantum research, I'll come into this, but today, that's out of scope for this class. Quantum gates. Let's see if there's a chart for quantum gates. That would be great. Is this it? They only have these 3? I doubt that it's the... Excuse me. I need to find a shortcut for... I need to set up a shortcut for muting. I'm assuming the gates are not as straightforward. Yeah, that's what I was expecting. And they're more matrix. It's a lot of linear algebra. It's like a hint of linear algebra. It's not exactly linear algebra. You have the XYZ, H, SPT, C0, CX, CZ, swap. C0, CCX, T off. I'm gonna put this as a later session. That's also out of scope. Alright, they're unitary operators. We do know what a unitary operator is now. A surjective bounded operator, which means that this is great, but this is a bit...
Your brain lights up like a TV when you're playing video games. So check this out. Researchers from the University of
Hang outside the room. Yeah, this is official. This is my official Christmas stream because I'm gonna be gone for the next 2 weeks. Yeah, I've heard. I never played Bayonetta. I've heard good things about it though. Yeah, unitary operators are surjective, which means that a quantum state is represented. I'm also, for next time, I'm gonna set up my iPad to go to OBS. Set up iPad. It's surjective. So you have the state of a qubit here. They are represented by a probability of each state. So when you have multiple qubits, it's a probability of all the different combinations of states. It becomes this very long equation. So surjective operator, the probabilities all add up to 1 before the operator is applied, and they also add up to 1 after the operator is applied, right? So you could think of it as a sense of linear algebra. I think that's probably also something that I want to go over at some point. It's just a linear algebra primer. That's also going to be important when I start talking about neural networks. Yeah, there's a lot that we can get into once we get into the actual signal part of quantum computers. It's very, very complicated. Unit vectors. This is, again, amazing, interesting stuff that we're not going to get into today. So what I want to stick with is no cloning at the moment. First, help me understand no cloning. Why does linearity and what else contributes? That was in ChatGPT. I don't know. Please don't pop up on that screen. I hate pop-ups that I can't predict where they're going to pop up. Is ChatGPT down? I can't get into ChatGPT. Alright, that's fine. And then let's get into quantum error correction. Well, I want to pull up. So this is what we're talking about. It's really hard to do error correction in quantum computers. So errors in quantum computation occur because of something called unexpected decoherence. So decoherence is you have the state that a qubit is in, a qubit being a 0 or a 1, these are the possible values, but a qubit is different from a bit in that a qubit contains the probabilities that it is a 0 or a 1, because you can't know for sure until you measure it. So that act of measuring it, when it's measured, breaks the possible states down and actually chooses the 0 or 1. You can think of it as it chooses which one to go to based on the probabilities. It's incoherence when we're uncertain of the state, and it's decoherence when the state is decided. Now it's still a qubit, but it is a qubit in a state of decoherence. Now, computation methods rely on coherence because what we essentially have is a huge number of probabilities, and then we have a way to check. Oh no, I'm gonna have to plug in my laptop. Great. We have a way to check the answer. We have a way to validate. This is really important in quantum computing. It's very similar to neural networks. You need to have a way to validate the answer. Which also would have been true with early computers. Now we trust that computers are making proper computations. So you calculate the probabilities and then you check them against the answer, and if the correct answer is included in the list of probabilities, you will give it interference, this positive interference, which makes the probability of some results higher and there's negative interference, which makes the probability of some results lower. And then you check again if the answer is included in the solution. And I think there's a bit more subtlety in this, like you might be actually checking the probability is on some level. I haven't gotten too deep into the actual computation part. And then you want to keep applying this interference. So the thing is, if you get decoherence in the middle of this algorithm, then you lose the state that you were in. This is kind of my understanding. I think there's a bit more that we need to that I need to understand about this. Like, can you go back to the same state you're in? But essentially, we need to have this probabilistic existence in order to find the final solution of a quantum computation. So it used to be on every quantum chip, then as you scale up in qubits, your errors increase. This makes sense, right? Willow is a big deal that increasing the number of qubits actually decreases the error, which I'm assuming is part of what they've programmed into the computer, that it's using other qubits to correct incorrect qubits or qubits that have undergone decoherence, or maybe it's a hardware part. There's some hardware component to this. So I want to talk about what causes decoherence as well. I'm going to talk about error correction. Like, how is it solving it? I'm going to talk about what causes the errors. But the first important thing here is, on a normal computer, now this is what I was talking about, the Apollo program and the Saturn V, they have multiple computers. When one computer it has a different result than the others. Let's say there's 4. I don't remember exactly how many there are. I wonder if there's a good article I can pull up. Apollo error redundancy. Apollo mission error redundancy. Apollo code redundancy speculation? No, okay, yeah, here's what they're saying. That's from WordPress. Let's find a better source. I don't want error codes. Apollo mission computation redundancy. The triple modular redundant system within the Apollo guidance computer. Yeah, this is what I'm talking about. Let's do the National Air and Space Museum. That seems like a good source. Okay. So this is a great example. Put all your eggs in one basket and watch that basket. Mark Twain, Pudd'nhead Wilson's Count. Yeah, that's funny. As the Apollo program took form in the early 1960s, NASA engineers were always kept safety at their astronauts in the fore in light. I can't even read today. At the fore in light of enormous risk, they knew they were going inherent in the goal of landing on the moon and returning safety. So whenever possible, they designed backup systems. So sometimes it wasn't practical. For example, service modules engines need to fire when the crew is behind the moon to place them in a trajectory. There's no practical backup if that engine fails, unfortunately. Apollo 8 carried no lunar module. This wasn't a practical solution, but during Apollo 13, the lunar module engine was used to help return the astronauts safely to Earth. There are numerous other examples of similar trade-offs that illustrates the need for safety against the need to venture. So here we're talking about IBM supplying computers for the navigation software. This is interesting. There's always been apprehension about the MIT guidance system to achieve the required reliability. So when you talk about the reliability here, you should understand that they're not saying MIT computers are unreliable. We're talking about a reliability that's probably something like 0.99999% reliable. But the fact is, if you're doing millions of computations, that's like, we're guaranteed to have 1 or 2 wrong answers. And modern computers are quite a bit more reliable, but they still, a lot of like, when you have a failure in your computer, that's a bug from a human who programmed it wrong. Um, that's partially what they're counting into the unreliability, but there's also just a hardware failures, and then there's like interference. So like computer bits can flip because of I think it's neutrinos can actually flip computer bits, and this gets worse when you get into space because you're outside of the magnetic sphere. So there's actually an example of an election that flip neutrinos. Is this it? Yeah. So this was in Belgium. Here, let me go to Wikipedia. In 1991, no, this is when they started. In 2003, here it is. One candidate got 4,096 extra votes. Do you see something interesting about that number? 4,096? It's divisible by 2. Whenever you see something, whenever you see a number divisible by 2, something's going on. This is going to be 2 to the 12. Yeah. So that means the 12th bit got flipped somewhere to add 4,096 error votes. The error was only detected because she had more preferential votes than her own list, which is impossible in the voting system. I don't understand what they mean. We're gonna avoid that. So one likely explanation for the error was a single event upset caused by a cosmic ray, which the voting system did not protect against. So this would be a cosmic ray actually went through the computer and flipped the bit. Anyway, the point of this is to show there's many different ways that a computer can fail. So you need software redundancy, you need hardware redundancy. So not only do we want multiple computers, but we want them to be running different software. We want them to be trying to calculate the thing, but written in different ways. We want also the computers, ideally, you have like each piece of software running on 3 or 4 different computer hardware. So if there's an error in that particular hardware, the idea is if there's a failure in the design of the computer, the hardware, there's a failure in the design of the software, that it's always, all the computers, the redundancy is going to fail at the same time, right? So you need different software, you need different hardware. I don't know if they actually have different hardware. I don't know if that's perfect. And then protecting against cosmic rays, I don't know much about that. Maybe it's random. Maybe there's some materials you can make the computer out of that protect. I'm not sure. Let's figure out. And probably just having a. Okay, hold on. I'm gonna get my charger. I'll be right back. system as secondary. The wisdom of the decision was proven during when the command module power was lost. Other machine onboard computers and navigation systems works perfectly. It also functioned reliably of the service module engine head towards Moon where there was no communication with Houston. The government envisioned this system guidance as a modest controller intended only to get the crew off the Moon and into lunar orbit where they would be rescued by the command module pilot. Cramming more... Wrote a provocative essay on cramming more components onto integrated circuits. Thus was born Moore's Law. The density of computer chips double every year, later stretch out to every 18 months. It's still ongoing 50 years later. By the way, it's not, actually. This is officially dead as of like 2020. Problem at that by the time they were flying in 1968, the 6-device circuit specified for the computer was way obsolete. Fairchild and others were supplying circuits that incorporated several hundred devices on a chip, but there was no way to test these new chips and incorporate them into the Apollo guidance. Okay, a lot of this is not really relevant. The thing I just wanted to mention was that this redundancy is a physical redundancy. You can just do the same calculations on 2 different chips. 3 different chips, and you can have 2 of them outvote 1. It looks like they don't use, or at least it doesn't really specify whether they use software redundancy. They didn't even necessarily use hardware redundancy, in that it sounds like they were the same 3 computers. Which I guess makes sense to reduce the amount of work you have to do to actually ensure they're all shielded properly from radiation and whatnot. But yeah, that's just the concepts of redundancy as a means to solve errors. In a physical computer are very simple. Just add more computers. Now, for some reason, on quantum computers, this is a very different concept. And that's what we're trying to understand. It's impossible to create an independent and identical copy of an arbitrary unknown quantum state. A statement which has profound implications on the field of quantum computing. This is an evolution of the no-go theorem authored by James Park, in which he demonstrates that a non-disturbing measurement scheme which is both simple and perfect cannot exist. I want, like... This is great. I want, like... techno. We need something high tech. 60 FPS shooter. I tried to play Marvel Rivals. I couldn't get it to work. My frame rate was hovering around like 7 or 8. It was completely unplayable. Which, I mean, I can play pretty much all other modern shooters. Obviously, I don't use a Mac. One of the best techno remix I know. Well, I don't know if yours... I'm assuming that's all DMC free. Power up more fun and catchy music. Oh, we can do that. Video game bangers. Nintendo EDM video game. Let's see. No, that's not quite what I'm looking for. Pops for locking in.
As I'm in the midst of applying for residency right now, wish me luck, Grammarly has again been a lifesaver with my application and helping me write my personal statement and CV. Grammarly is your digital writing assistant. It's an all-in-one tool that improves your productivity, triple checks your work, and saves you time when working on multiple assignments. Even the free...
Oh wait, you know what? There's a good PlayStation like breakbeat. Is that the right word? Jungle is jungle. Though polyracemist is something like this. I don't think any of these are exactly what I'm looking for. Ethereal bricks. Yeah, this is it. Just give me a second to make sure. Games featured. No, these are using video games within our music from video games. No. No, that's real music. These Sekia sessions, these are very, very good. I think they're... I don't know about their copyright though. Well... No, I don't know. I don't know any of these. Okay. Here. 3, 2, 1, go! Oh. You're just gonna go for the Gran Turismo. Suppose we have two quantum states, A and B, with a common Hilbert state. Hilbert space H equals HA equals HB. Suppose we want to have a procedure to copy the state of quantum system A over to the state of quantum system B for any original state, that is, beginning with the state. We want to end up with the state A. Okay, so quantum system B has this probability for state B. We want to end up with the state okay. To make a copy of the state A, we combine it with system B in some initial or blank state independent of which we have no prior knowledge. Actually, I think I'm understanding this. The state of the initial composite system is then described by the following tensor product. A and P. The following we omit the X symbol. That's like bracket notation. It's a rock notation. There's a notion for linear algebra and linear operators. Okay, let's learn this in a future stream. Suppose we have two quantum systems, A and B. There are only two permissible quantum operations with which we may manipulate the composite system. We can perform an observation which irreversibly collapses the system into some eigenstate of an observable, corrupting the information contained in the qubits. This is obviously not what we want. Alternatively, we can control the Hamiltonian of the combined system, and thus the time evolution operator for a time-independent Hamiltonian. Evolving up to some fixed time TO yields a unitary operator U on H next to H, the Hilbert space of the combined system. However, no such unitary operator U can clone all states. What's a Hamiltonian? Hamiltonian. In quantum mechanics, a Hamiltonian is a system of operator corresponding to the total energy of that system, including both kinetic and potential energy. Its spectrum, the system's energy spectrum, or a set of energy eigenvalues, is a set of possible outcomes obtainable from a measurement of the system's total energy. Due to its close relation to the energy spectrum and time evolution of a system, this is too loud, right? Due to its close relation to the energy spectrum and time evolution of a system, it is of fundamental importance in most formulations of quantum theory. So its operator corresponds to the total energy of that system. Okay. Schrödinger Hamiltonian. So H is kinetic plus potential. Potential is like based on the state and time. Okay. I mean, I'm gonna say that makes sense. Control the Hamiltonian of the combined system. That's the time evolution operator. Mathematical formulation of quantum mechanics. We're going to need to get into some very complicated states topics to get a full understanding of this. Description of the state of a system, measurement in a system, description of physical quantities, result of measurement, effect of measurement on the state. Spin. I feel we're getting... The topics are exploding so much faster than they exploded last week. Okay. That's the time evolution operator. So I guess the time evolution operator are those... Well, wait. Let's just find it here. Time evolution of a system. Though it is possible to derive the Schrödinger equation, which describes how a state vector evolves in time, most texts assert the equation as postulate. Common derivations include the de Broglie hypothesis or path integrals. So postulate 3, the time evolution of the state vector is governed by the Schrödinger equation where ht is the observable associated with the total energy of the system. Equivalently, the time evolution postulate can be stated as the time evolution of a closed system is described by a unitary transformation on the initial state. So the initial state is represented as this, v at t0, and then the time, okay, and then we get the state at t. Okay, this makes sense, right? This is the initial state, this is the operation, this is the resulting state. That's the time evolution operator for a time-independent Hamiltonian. What do they mean by the time-independent Hamiltonian? Because the Hamiltonian already... Here, I need to write this down. The Hamiltonian already includes time. It includes the measurement of the energy across all time, the potential and the kinetic. Total energy. Then we have a time evolution operator. Evolving up to some fixed time t0 yields a unitary operator u, the Hilbert space of the combined system. However, no such unitary operator can clone all states. So this is what I'm not getting now. Answers the following question in the negative. Is it possible to construct a unitary operator acting on... Okay, so what is this? The Hilbert space of A over B equals HH. So, does this mean because we don't... We don't know the total energy of the computer B? We don't know how much energy... We can't take energy from A to add to B? That doesn't make sense. Why couldn't we add it from like a third computer? I don't think I'm understanding that correct. There's no unitary operator U on the Hilbert space such that for all normalized states A and B and H... Okay. I'm definitely going to need to understand this notation. So this was the initial state for A and the initial state for B. There's no unitary operator U. Just that for all normalized states equals... This is the state of B evolving over time, create A and B. Okay. I don't understand it, but I think I understand what I don't know here. And to get this, we're definitely going to have to dive into these unitary operators quite a bit more. First of all, let's just get a Hilbert state. Consequences, no cloning theory, prevention, yeah. Projective Hilbert space. I'm intrigued by the photo here. The visual effect of perspective where parallel lines seem to meet at affinity. Projective space may thus be viewed as the extension of a Euclidean space. Okay. What I want is Hilbert space. I need to know what a Hilbert space is. Type of topological vector space. Mathematics Hilbert spaces allow the methods of linear algebra and calculus to be generalized from finite dimensional Euclidean vector spaces to spaces that may be infinite dimensional. Okay, Hilbert spaces arise naturally and frequently in mathematics and physics, typically as function spaces. A function space is a set of functions between two fixed sets. Okay. Often the domain and or codomain will have additional structure which is inherited by the function space. For example, the set of functions from any set X onto the vector space has a natural vector space structure given by pointwise addition and scalar multiplication. In other scenarios, this function space might inherit a topological or metric structure, hence the name function space. The set of functions has a natural vector space structure. Okay. That actually makes sense. So it's saying to do the calculation between a fixed set into a different fixed set. I guess this is just the basis of algebra. This is the operator you apply on one set to turn into another set. Is that correct? Here, let me start a new chat. Is that the right way to think of it? No. We use functions or mappings to go to one set, but the term function set isn't standard terminology. The key concepts for mapping between sets: linear transformations. There's special functions between vector spaces that preserve vector addition and scalar multiplication. Linear maps, another name for linear transformation. Wait. So what is a function set? Oh, sorry, function space. Jesus. Can I do the ChatGPT thing? Function space. I want to start this chat over. Yeah. Function space is not an operator, rather it's a set or space whose elements are functions. Sure. Just like how we can have a vector space of vectors, we can have a space made up of functions that satisfy certain properties. The space of all continuous functions in an interval. Okay, so. No, wait, I don't want diagrams. No, quick draw with Google. Dot with Google. Draw shorts.
I see square. I see door. I see cell phone or telephone. I have no clue what you're drawing. Sorry, I couldn't guess it. I see ocean, or line, or canoe, or table, or banner. Oh, I know, it's hot tub. I see triangle, or star, or diamond. Oh, I know, it's ice cream. I see circle. I see dumbbell, or glasses, or garden hose, or the Great Wall of China. Oh, I know, it's motorcycle.
China?
I see street light, or stairs, or chair, or lipstick. Oh, I know, it's church. I see circle. I see hula hoop, or bracelet, or cherry. Oh, I know, it's scissors.
Very cool. That's not at all what I was looking for. Sketch.io. So the way I see it, we have a 3D space here. Alright, and let's say there's... Dude, this background is wild. There. Here, let's put a star. Okay, that's gonna take too long. And then you have spaces spread out in this vector space, right? These are points in, sorry, it's not a vector space, it's just a space. Do you see what I'm saying? So now we have 5 by 3 by 2. This is a space. One set starts here, one set starts here. You have 1, 2, 3, 4, 5. And then where these meet, this is on the bottom. And then you see this goes up to here and up there, and that's 3. I mean, it's messy, but... So a vector space means each of these points in this space is a vector, right? They can be independent vectors in different directions. Like this. How did that dot get over there? It would be about here, realistically. But yeah, you get the point. Each of these points in this space has a vector. So to go from one vector space to another, we multiply by a function set, right? Sorry, a function space. So it's just a space of functions. So like now each of these locations is a function. And we multiply by one set of vectors, we multiply by the functions, gives us another set of vectors. Cool. So that's a function space. So a Hilbert space is a vector space equipped with an inner product that includes a distance function for which the space is a complete metric space. Wow, okay. Equipped with an inner product. The inner product is a real vector space or complex vector space with an operation called an inner product. The inner product of two vectors in the space, often denoted with angle brackets such as AP. Inner products allow formal definitions of intuitive geometric notions. Okay. A metric space is set together with a notion of distance between its elements. Okay, for which the space is a complete metric space. A metric space is called complete if every Cauchy sequence of points M has a limit that is also in M. Cauchy sequence is a sequence whose elements become arbitrarily close to each other as the sequence progresses. More precisely, given any small positive distance, all excluding a finite number of elements, the sequence are less than that. Since definition of Cauchy sequence only involves metric concepts, it is straightforward to generalize it to any metric space X. To do so, the absolute value is replaced with distance dx. I don't know what M to N is. The most familiar example of a metric space is three-dimensional Euclidean. Okay, so metric space is just space. It has distance. Called complete if every Cauchy sequence of points in M has a limit that is also in M. Oh, okay. So just every... What is a Cauchy sequence? A sequence of elements become arbitrarily close to each other as the sequence progresses. Okay. So we're talking about a space of vectors where every vector terminates in M. Like everything covered by every vector and every function, it's all in the same metric space. We're not going outside of this metric space. Includes with a distance function for which the space. A Hilbert space is a vector space equipped with an inner product. Thence I think I don't understand. What does it mean to have the inner product in a vector space that includes a distance function? Or the inner product in Hilbert space. The article on Hilbert spaces has several examples of inner product spaces where the matrix is induced by the inner product yields a complete metric space. Example of an inner product space which includes an incomplete metric is the space CAB of continuous complex valued functions f and g. On the integral AB, the inner product is space is not complete. Consider, for example, for the interview -1 to 1, the sequence of continuous step functions. The sequence is a counting sequence for the norm induced by the preceding inner product, which does not converge to a continuous function. Yields a complete, and the metric induced by the inner product yields a complete metric space. Okay, just give me in a normal function space. Hilbert space is actually a special type of function space with additional mathematical structure. It's a complete inner product space. It's a complete inner product defined to it. A way to multiply functions together and get a scalar. So it's kind of like multiple spaces. Does this make sense? And a function, maybe not a function, maybe a vector is the right word. Each point is a function. Sorry. Think of it in this way. In regular 3D space, points are x, y, z coordinates. So Hilbert space, each point is an entire function. I got that. The inner product is a tool we have to measure relationships between these function spaces. For example, in one point might be sine x, another point might be cosine x. The inner product lets us see how these relate to each other. In this case, sine x 0. This tells us these functions are orthogonal to each other. So, how does each point have its own inner product, or the entire space shares one inner product? Or it's a set of functions which make up an inner product? I guess I don't fully understand what an inner product is. Let's use one inner product operation. Let me make this very concrete. Hilbert space, each point is a function. Let's take the inner product of any two functions in space. We always use the same operation. We could do. Okay. Nope, I got it. That makes sense. Awesome. Okay, so let's go back to the no cloning. Let's see, where exactly the Hilbert space evolving on the yields a unitary operator on the Hilbert space of the combined system. time evolution operator for time. Is it possible to construct a unitary operator? This will be always evolves into the state regardless of state system. So because you can't just set values, you need an operator, and we can't read. Okay, let me ask Cloud. Whoa, I get one more message? You know what? It's okay, I've been on for over an hour, so let's just make this last message a good one, and then I've gotta go do some birthday stuff. Because you need operators to transfer. I want to make sure I'm asking the exact right thing. A is Hamiltonian. The time evolution operator for a time independent Hamiltonian. So right, we got really deep really fast today, so I'm already kind of exhausting myself mentally. Let me break this down carefully. No cloning theory comes to two fundamental aspects of quantum mechanics. Linearity is fundamentally linear. Any operation we could do must preserve this linearity. Say we had a hypothetical cloning operator that could clone any state due to linearity. If we could clone, we must be able to clone superposition A to B. I think the big thing, the big problem is not understanding bracket notation. I think that would help me a lot. Yeah, so I mean, I get it. It has to clone this value, this point, and this point individually. It needs to be able to clone them together. So if u clones 0.1, then u 0.10 equals u1 u1. So that might exist, and this might exist, but together equals probability of the operator. This is 0.1 equals 0. Oh, so it's the probability, so it becomes the probability of both points plus the probability of both points, not an individual. In terms of linearity, which will not moves, clones, superposition, because the result would be the combined probability of both points having the same value instead of the probability of each individual point having the desired value. All right. Let me address each part of your thoughtful questions. On mapping spaces, you're onto something interesting. The core issue isn't about mapping between spaces, but rather we're trying to create a function that would need to take an arbitrary input space, yeah, create a copy of its space in B, maintain the original space in A, do this while preserving quantum mechanical properties. I got that, yeah. The problem isn't just that we can't know the state, though that's relevant. It's that no such unitary operator can exist that accomplishes this for all possible input states while maintaining quantum mechanical constraints. Yeah, I'm interested in what are the constraints that break down. What are the constraints that break down during cloning? I'm just taking this note for next time. Oh, I never turned my camera back on. Hello. Adjusting the Hamiltonian means modifying the energy operator that describes the system's evolution. The Hamiltonian determines how a quantum system evolves over time through the Schrödinger equation. When we talk about adjusting it, we're typically referring to changing the energy levels of the system, modifying the interactions between components, adding or removing terms that represent different physical effects, controlling the system's dynamics. And this is a could adjust. So we're talking about the combined system. We adjust the energy level of the combined system, modifying the interactions between the combined system. Yeah, okay, so that would be applying an operator, an energy-based operator between all points in the space. Adding or removing terms that represent different physical effects. Okay. Just adjusting the energy in some way. What was that? It is impossible to perform an operation which closes because the result would be the combined probability of both points having the same value instead of the probability of each individual. Yes, exactly. You've hit on a key insight. The problem is that linear operations preserve superpositions, but cloning a superposition state should give you the tensor product of the state. Yo, you're losing. You're telling me I'm right, and you're losing me. The problem is that linear operations preserve superpositions, but cloning a superposition state should give you the tensor product of the state with itself. Linear operation on superposition is the probability A plus probability of B. What cloning should do okay, wait, so we're multiplying the probability of A to 0 plus probability that it's 0 to the probability that it's 1 equals the probability of the operation on 0 plus the probability of the operation on 1. What it should do is the probability of 0 plus probability of 1 cross product, that's cross product. Probability of 1 equals A squared probability of 0 plus AB probability of 1 plus AB I don't understand this. This is the only everything up until here I don't understand. I mean, I get this equation. What I don't get is what's the operator? Where's the operator here? I'm gonna come back to that. Alright, I'm gonna come back to that. I am going to wrap up for the day. Alright, we made it to the first bullet point again. Good job. I realized there's a lot more linear algebra in here than I thought. I mean, I knew it was going to be very mathematically heavy, but my linear algebra just isn't there. I actually never really took it. I had to learn it for my master's when I did neural networks, and I've forgotten pretty much everything I've learned. So I'm hoping to brush up on it so that I can really understand what's going on the actual mathematical level, which is what I'm not getting right now. Alright, I'm curious, what is their roadmap? Beyond classical. 2019, physical qubits, 54 physical error rate. Quantum computing in 28, they were able to demonstrate. Oh, so this is just when they demonstrated that it actually works. Performed a target computation in 200 seconds, that would have taken 10,000 years. Yeah, sure. This is very similar to the time computation gains that they're talking about in this last release is just an evolution of the gains they released here. So the breakthrough of this one is error correction. We define a long-lived as one that is capable of performing 1 million computational steps with less than 1 error. Large error-corrected quantum computer. So, look, if this is 4 years that they've only been able to prove error correction, we're not even yet to the scale-up sense. Physical qubits, we got 100. A long-lived logical qubit. I don't understand why that's a problem. They're expecting error rates to drop. Error-corrected. Needs both logical qubits and the ability to control these qubits to perform quantum gates. Oh. So we don't even have quantum gates yet. And then we scale up And then we have a real computer. Is that the size of it? Wow. Anyway. I need a farewell scene. I'm gonna be gone pretty much the rest of December. I'm gonna be doing a bit more of this on my own, and I'll get back into it in January. Hopefully, I will be able to jump into. There's a place where you can actually do test bed.